So in the last lecture, we looked at algorithms for initial value problems. Okay. You're here. I'm saying after a long time. How did it work for you?
It worked really good. I'm working nights right now, so I'm able to come in.
Okay. All right. But online was all right. Okay. So we introduced a lot of important concepts, and I just highlighted them in the review section. Remember, I told you last time for your exam, you should be able to engage in a meaningful discussion on any of these topics in the oral exam. So we started by saying what is the difference between autonomous and non-autonomous systems for system of ordinary differential equations. So dy dt equals f of y comma t. If t appears explicitly in there, then we would call that as a non-autonomous system. T doesn't appear, then it is an autonomous system. The main difference is if it is autonomous, then translation in time doesn't change the solution. So if you have a trajectory, you can pick your initial condition on anywhere on the trajectory. The rest of the trajectory will remain the same. And then we looked at the implicit versus explicit methods. And the implicit methods always require the next predicted time step value. So that value is implicit in terms of going from yn to yn plus 1. So this is the current step at yn, and this is what we want to predict, yn plus 1. So we can predict that yn plus 1 without having to iterate, then we have an explicit method. And if yn plus 1 itself appears on the right-hand side, then it becomes an implicit method and need an iterative solution procedure. This has nothing to do with the iterative versus direct method we saw for solving a system of linear algebraic equations. Those are two different methods for solving algebraic equations. This one simply refers to our ability to predict the future knowing only the current, which is an explicit method. And if you need to know the future is, then it's an iterative algorithm at every time step. And such algorithms tend to do a good job in handling differential equations. So we talked about what are stiff differential equations and why implicit methods are good. And in that context, we then looked at the stability of numerical stability of the algorithms. So we found that the explicit methods typically have a stability bound in terms of the step size. You cannot choose arbitrarily large step size because the numerical method will blow up, even though the physical system governed by this equation remains stable with numerical instability. And you need to be able to detect whether something is caused by numerical instability or physical instability. And these apply to dynamical systems, okay, when you're integrating an ordinary differential equation of this type. And we saw how we can pair explicit and implicit method to form this predicted corrector pair. And then we looked at single step versus multi-step methods. We are in the process of reviewing the development of multi-step methods. Today I will move to the single step methods, and then we will move on to the other topics. And the other concept that we talked about is the local truncation error versus global truncation error. The term that is neglected in the series gives you the local truncation error per step in going from n to n plus 1. But that error will be accumulated going from n plus 1 to n plus 2 to n plus 3, etc. And that accumulated error is what we call the global truncation error. The larger the step sizes, the larger the number of steps, that error will continue to increase. Here maybe a question for you. If you understand all these concepts, you should be able to engage in a discussion on this question. The question is the following. Okay? So I have dy dt equals f of y. Let's take for the moment that it is an autonomous system. So there is a potential for autonomous systems to reach a steady state. Non-autonomous system, time always appears, so it's going to be driving. So there may not be a steady state solution because you are driving the system, you are forcing the system, typically in control applications. But if you have an autonomous system like this, why do I say that there is a potential for it to reach a steady state? Because there is also the potential for it to have a periodic state, right, through a half bifurcation point, or a chaotic state. Okay, so essentially, a system that evolves in time can reach a steady state or can have sustained oscillations or chaotic response. Now, for such a system, when I have dy dt is equal to 0, okay, if there is a steady state, I get the steady state solution by solving that, right? And that means when I'm plotting the function y versus t, I might get something like this, and then it reaches a steady state, right? Now we're talking about accumulation of errors, right? When I have a Euler method, just order h error, or modified Euler method, order h square error in that. So every step we say that there is an error, and the error accumulates. Okay? So the question is, what would happen to the error as t goes to infinity? It shrinks to 0. Why does it shrink?
Because the next, like each time you guess, you're going to have, if you're basing on the previous guess, it's a different chain. There's not going to be a very large error or no error.
But does the error then remain constant? That is, suppose you are able to, you take a differential equation and you are able to solve it analytically, and you have a curve, and then you are doing it numerically, and you are putting points on the curve. Okay, and you can also solve the steady state problem analytically, and you will get one point at the end. That's a steady solution. So the idea is that the dynamical system, if it has a steady state, will settle down on the steady state. Right? If the steady state is stable, it will settle down on the steady state. Right? So what is the mechanism that gets rid of the errors? Because this algorithm that I'm going to use will introduce an error at every time step, and that keeps accumulating. If I integrate it for long enough, will I get the steady state predicted by this, or will it have an error? Is there a mechanism that you can identify where that error is gotten rid of? This really asks you to think about what are the sources of the truncation error. And so when we did the Taylor series expansion, we said the truncation error has the neglected term, the term that we call of order, has two parts. One is the step size itself, which you can control. The other one is the derivative. So if in the fourth order method, you might have a fifth derivative multiplied by h to the power 5 or something like that, right? What happens to the derivative as it settles down on a steady state? It goes to 0, right? So that's the mechanism that allows you to kind of cleanse itself. So you will, this is a way of getting steady state solution, time marching to sufficiently long time so that you get a steady state. And so if the steady state, if you had some initial condition, you can think of it, and there is what I'm trying to point out, and this is something that you will experience. Every one of you will experience if you are using COMSOL at some stage, okay, or any simulator for that. In the iterative process to reach a steady state, what do we call the initial value that we give? An initial guess. An initial guess to the problem, and Newton method gets rid of that error in the initial guess and gets you the solution. Okay. In a dynamical sense, this is an initial condition, right? So for a dynamical system, every point on the solution is a meaningful solution to that differential equation. Okay? But in an iterative sense, that's an initial guess, and the subsequent guesses you cannot be interpreted as anything meaningful, except the iterative scheme would be such that it gets rid of. And the fixed point view tells us how the iterative process gets rid of those errors to get to the steady state problem, the solution to the steady state problem. Okay, so the reason why a dynamical method like this, even if you use a very large step size, and this is a trick that is often used, I'm interested only in the steady state, okay, and I want to use a dynamical integration scheme, but I will use a very large step size, but I will use an implicit scheme so that stability of the numerical method is preserved. And since I'm not interested in the entire trajectory, I can take a large step size and sustain a lot of errors on the way to the steady state. But once I reach the steady state, it's called pseudo-transient method to get the steady state. Okay, so you might come across this terminology, a pseudo-transient method. The other consequence of this is when you're using, and you will find that also in solving Navier-Stokes equation in COMSOL, if you choose to formulate a problem as a steady state, for example, this morning with Santiago, we were talking about flow past a cylinder. Okay, so if you're doing the simulation for flow past a cylinder, and you do the simulation around the Reynolds number of 160, but you choose that it's steady state option that you have made, stationary. Okay, what would the numerical method do? And that condition of Reynolds number, there is no steady state solution. They're stable. Okay, so you're asking it to use the steady state algorithm, the Newton iteration, for example. Okay, either it blows up due to numerical instability, or the iteration will oscillate. Okay, so that's an indication that you need to do a dynamical simulation properly to get the true dynamic response. Otherwise, the iteration will never converge, and you will see that the error going down and the error going up and the error going down and up like that. Okay, so there is kind of a similarity between the dynamical integration of a dynamical equation and an iterative way of solving a steady state equation. And so the pseudo transient method is one that is often used to find steady state solutions. Okay? But the reason why the steady state solution will be accurate is because the part in the truncation error that has to do with the derivatives, they all go to 0, even though the step size is fairly large. Okay, so we'll still be able to get accurate result. I just want to check how the guy is doing it. Yeah. Okay, at least some of them have shown up. Maybe it's a holiday for them. So in the very end of the last lecture, I think we were talking about multi-step methods. We developed a whole range of multi-step methods, and the basic idea to develop multi-step methods is to use the Newton backward polynomial, using the backward operators that we see here. Okay, and they then tend to couple the points behind them. Okay, depending on how many terms in the series that you take. And we saw a 3-point and a 4-point backward difference method that were explicit. And I think the point where I talked about is how do we generate implicit multi-step methods. Okay, and the idea is very simple. All you need to do is use still the same approximation for the function in terms of a polynomial, but choose your reference point to be Tn plus 1. That is the next step, the future step that you want to predict. Okay, construct a polynomial from that, but using points behind it. So Tn plus 1, Tn, Tn minus 1, Tn minus 2, etc. And if you use a backward difference polynomial with that as your reference point and truncate it at a suitable position, maybe second, third, etc., you will get a whole class of implicit multi-step methods. Then what you can do is you can pair an explicit multi-step method with an implicit multi-step method to form a predictor-corrector pair. Okay? And all these ideas can then be programmed into codes like ODE45 or RK45 and things like that. Question? Are you able to see this all right? Do you want to write it down or? Yeah.
Is a predictor-corrector method just an implicit? Is it like a subclass of implicit methods? I guess I'm having trouble distinguishing the two, because an implicit method to me still seems like a predictor and then a corrector.
Right, yeah. Okay, that's a good question. If you choose to use only an implicit method, you don't call that as a predictor-corrector, because the best that you can do for your first prediction of the unknown yn plus 1 is to assume it to be the same as the previous one. Okay, so you are solving a set of nonlinear algebraic equations at every time step. Like, let me just show you this particular one. So here I have n plus 1, n minus 1, n minus 2. Four points are coupled,
right.
But I need to calculate fn plus 1. So I need to calculate I need to know what yn plus 1 is.
Right.
Okay. So if I didn't have an explicit method paired with this, how would I solve that? I'll just make some guess. What is the best guess that I can make? I can say it's the same as yn. Okay. So I can take yn, put it into this function, and put it into this function, and then for yn, fn minus 1, fn minus 2, I will use the right one. Okay. And then I need to iterate, because this will predict the yn plus 1, and I will take that and plug it back in here. Okay. And that loop is the same as in the predictor-corrector method, but I'm not pairing it with any other method. I'm just making an initial guess. Now, what the predictor-corrector pair means is, if this is of order h to the power 5, I need to find an explicit method which is of the same order as h to the power 5. And there is one that we developed already in the previous class. So that will predict the first one, which is going to be better than it's the same, or it's going to be better than it's going to be a tangent projection, which is what we do in Euler, simple Euler. And so by fitting a higher degree polynomial, essentially in all these what you're doing is, if you have 4 points, you are fitting a third degree polynomial, and then using that to predict what the next value will be. So the initial guess will be much more closer to the actual solution. And so you get the answer in a few iterations. The better the initial guess, there are fewer iterations that you need to do. Okay? Good question. Yeah. Okay, so this method, we truncated it, I think, up to delta cube term. Took up to delta cube term and then neglected the next delta to the power 4. So the truncation error in the polynomial is of order h to the power 4, but because of the integration, we will get another h out of that. Okay, so the truncation error is of order h to the power 4, like you see here, and when you multiply dt with h d alpha, you'll get h to the power 5. So that's a very accurate implicit multi-step method. But we already talked about the problems in not being self-starting. Any multi-step method cannot be used from time t equal to 0 because we have only one value. It demands, in this case, 3 previous values, okay, n minus 1 and n minus 2. And so you need to generate the first 2 values, and then you can switch to this. Step size control ideas. These are very heuristic. There is really no theory. At least in developing the algorithm, there is a polynomial structure. Yeah, sorry. Thank you. Okay, in developing the algorithm and doing stability analysis, etc., there is a formal procedure that we use to systematically develop the whole class of algorithm. But step size control, there's really no magic to it, no theory to it. It's just ad hoc. Whatever you can come up with and implement it and see whether it works or not. And over a period of time, these have become robust enough that they are automatically used in MATLAB routines. And I think even COMSOL has automatic step size control, right? And what is automatic step size control? It's essentially, I think Tom asked last time, how do you estimate the error? You need at least 2 different ways. Okay? One is the embedded idea that I'm going to talk about in the Rangakata method. But with multi-step methods, single-step methods, the idea is you make 2 estimates of the error by using different step sizes. So you use h and you predict, and then you use h over 2. So you take 2 steps and then compare the 2 results. And if the 2 results are in agreement, compare the tolerance that you specify, that step size is fine. Okay? But if they are too small, meaning your tolerance is 10 to the minus 4 and these results differ 10 to the minus 8, that means your step size is too small. So you can take a larger step size. So the next time around, you double the step size. Okay? And of course, if the results do not agree to the tolerance, what do? You reject that result, you go back, you already have the result for h over 2, you do h over 4. So and then compare that. You do the division like that until it agrees. Because you have to put a bound on both sides so that h doesn't become too large or h doesn't become too small. So in all these algorithms, you will have these options that you have to specify. Okay, so in MATLAB, for example, ODE45, there is an option structure. In that, you will find you can specify the tolerance, you can specify the minimum step size, you can specify the maximum step size to implement this heuristic idea. So here, we're talking about implementing the 4 step. Okay, so in order to predict y4, you need y3, y2, y1, and y0. Okay, so it's a 4-step process. So the first 3 steps you must generate using some other method. Okay, and these are Euler method. The first step can be only by Euler method or modified Euler method. Then you can have a 2nd order method. Then you can have a 3rd order method. And then you go to the 4th order method, and then you say, okay, I'm happy with the 4th order method. I'm going to continue to use the 4th order method from that point on. Okay, and so this is the point where you can first begin to use the Adam Bashford, Adam Moulton schemes. And so all the circles are the ones that you would use with the original step size that you have chosen. Okay, if the results are agreeable, then you can continue to use the constant step size and go on. But in going from here, for example, to predict Wi-Fi, I take an intermediate one and compare. So Wi-Fi I'm predicting in two ways. One is directly using the step size h, another one is using h over 2. Okay, and I would compare that. And if the results are just about the tolerance, then I would continue to use the step size and move on. Okay, but it might happen that the results are extremely good. That means I'm allowed to take the step size, increase the step size. Now, can I increase the step size from here to here? I would have difficulty because if I increase the step size in going from here to here, I need to find 3 values in the past, right, with the step size of 2h, and I don't have them. Okay? So you need to delay when you can increase your step size. Okay? So possible to double the step size only from this point on for that particular algorithm. Okay? Halving the step size you can do anytime. Yeah.
In the same way, though, when you have the step size, do you need to go back and calculate y 3.5 and y 2.5?
Right.
Do you have to go back and do those, or?
No. You don't go back to do those. So that's why you can use the corresponding interpolating polynomials. So if I have an Adams method that is of order h to the power 5, I also have an interpolating polynomial for y. Remember, there's a distinction. What we are trying to predict is y, but what we know is the function f, right? The Adams method requires you to calculate the function, but it is a y value is the solution that we need. So if you have solution at sufficiently large number of points, you can fit a polynomial and generate those numbers at the intermediate, because the errors should be the same. You need to match the h to the power 4 or h to the power 5 in the interpolating polynomial and in the algorithm that you're using. Okay? So it's a very simple heuristic idea like that that is normally implemented in controlling the step size for higher order methods. So the bookkeeping becomes a bit of tedious problem, but it's not a challenging concept. I have one that's coming up later today. It's really a challenging and a beautiful concept, so I thought I should talk about it even though it may go over the head. We'll get there, and I'm going to write it down because I haven't prepared the notes for that. But any other questions on this? Rangakata method. What are Rangakata methods? Those are also methods for solving ordinary differential equations, initial value problems. And the Rangakata methods have a kind of a structure that is different from multi-step methods that we developed from the polynomials. So the basic idea here is I'm going to develop or propose a structure for formula that will allow me to predict yn plus 1 from yn of any order that I want. Okay? So when I say any order, what does it mean? The truncation error of order h to the power 4 or h to the power 5. And I'm going to achieve that by suitably weighting some function called k. So wi is a weight factor here, and k's are the functions. If you look at k is nothing but the step size multiplied by the function that appears in the differential equation. But the function is calculated at different locations between n and n plus 1. Okay, so I'm going to take the step. Okay, so I'm going to take the step in going from n to n plus 1. So Rangakata methods are single step methods. They advance only one step at a time, but they improve the accuracy. They make it possible to improve the accuracy by evaluating the function at a number of intermediate points. And these would be called k1, k2, k3, etc. Okay, and we are identifying where those functions will be calculated. So this is a function. Remember, the function is, this is for, in general, non-autonomous systems. So the function is a function of t and y. Okay, so this is the equation that we are looking at. dy dt equals that. Okay, so the function is evaluated at the current value of tn plus some intermediate time steps between tn and tn plus 1, and the function itself yn plus a weighted average of the functions in the previous part. So this was a proposal by Ranga and Kata, two German applied mathematicians, I guess. So what we notice in here is that we have introduced a number of parameters. C, wi, and aij are yet to be determined parameters in that algorithm. So if I put numbers for those, then I have a systematic way of predicting yn plus 1 from yn. First thing is I would calculate all the k values I need, and put in the k values, and I predict yn. Okay? So once again, it's possible to have explicit versus implicit methods. We have for explicit methods the same stability bound issue. And these coefficients are often organized in a table like this. So the C's are the coefficients that go with the time, but they are organized in a row like that. And the W's are the weight factors that go in the original equation. And then Aij are the weight factors or the K values that go into that function. And our task in developing the algorithm is to find what are the best values for these numbers, C1, C2, C3, C4, etc. So you need to choose, for example, how many steps do you want? You have a two-step Runge-Kutta method, two-stage, three-stage, so single steps, okay, going from n to n plus 1, but it's called a two-stage or a three-stage, and that is determined by this V. It says how many intermediate K values you need to evaluate. So if V is 2, I have a two-stage Runge-Kutta method. I will need to calculate K1 and K2. If V is 3, then I need to calculate K1, K2, and K3. I have a three-stage, but a single-step method. Okay. So we want to see how we develop these coefficients. How do we develop these algorithms? Now, if the structure is fixed in such that Aij, the coefficients in that matrix Aij are all lower triangular, then we have an explicit method. Okay, that means in calculating K1, I don't have K1 on the right hand side. Okay, so if I'm calculating K1 for I equal to 1, I will not have K1 here because the summation stops at the previous part. Okay, so when I'm calculating K2, I might have K1 appearing here, but not K2. If K2 appears, then what happens? It becomes an implicit method because this is a nonlinear function, right? So the unknown appears on both sides. That makes it an implicit Runge-Kutta method. They call it a semi-implicit Runge-Kutta method if only Ki appears on the left-hand side when you're calculating Ki. That is from 1 up to Ki. If it appears only from 1 to Ki minus 1, it's an explicit method. If it appears such that it's 1 to Ki, it's a semi-implicit method. If it has all the values from 1 to V, okay, then it's a fully implicit method. What does that mean? When I'm calculating K1, and not only I need K1, but I need K2, K3, etc. So if I have three-stage Runge-Kutta method, I will need to solve for K1, K2, K3, right? So in calculating K1, I will have on the right-hand side all of them, K1, K2, K3. Calculating K2, I will have the same thing. I actually increase my size of the block 3 times. Okay, so that's a fully implicit method. So they are not often used because it increases the computational load significantly. Semi-implicit methods have been developed in the 70s by some prominent chemical engineers because they are good in stiff systems, and we deal with stiff systems in process reaction engineering. Any questions on the general idea of what a Runge-Kutta method is? You need to understand the structure, how the algorithms are developed. Okay. RK45 is a good example in MATLAB. It's a very popular and powerful method. So in this framework, I should still be able to generate my original Euler method, the modified Euler method, etc. So how does one go about it? I'm taking V equal to 1, a one-stage single-step Runge-Kutta method. Okay. So then I expand the formula that I have. So Yn plus 1 equals Yn plus W1 K1 because I have only one stage, only K1 to calculate. Okay. And K1 will be given by H times the function evaluated at the end Yn. That means I'm saying C1 is 0, another A11, A12, they're all 0. Okay. So if you go back, you should be able to understand how you would write this from, and in the book by Lapidus and Seinfeld on ordinary differential equations, you'll find algorithms after algorithms, Runge-Kutta method, the numbers given in this form. So if I give it to you in this form, you should be able to say, okay, I can take this and plug the numbers into the defining structure that you have above and write out this explicit specific form. And then I can take it to MATLAB and code it if I need to. But these days we really don't need to because there's no point in reinventing the wheel. These codes are already being developed. But we want to understand the ideas that go behind developing what are the best values for the coefficients. So in this particular case, there was only one coefficient that I need to find out, W1. Okay, so how would I do that? So here I have a formula, Runge-Kutta method, one-stage Runge-Kutta method, and I want to match this solution with the Taylor series expansion. Remember when we started talking about initial value problems, we posed the problem in the following way. I truncate it here, and I get the Euler method. And we said, why can't I truncate it here? The problem was I needed to calculate the derivative of this function, second derivative. But what is the second derivative of the function? It is the derivative of f, right? Because dy dt is equal to f. If I want d square y dt squared, which is what this term, same as df dt. But f is something that's going to change for every problem, right? So if you're going to use this idea to get more accurate results, every problem I need to take the derivative of the function. I don't want to do that. So the Runge-Kutta method is a clever way to avoid that and still get higher order accuracy. So the way that we do that is, okay, I'm going to truncate it, for example, second or third term, and see that I can match the Taylor series term by term with the formula that I get from the Runge-Kutta method. That matching process is the key idea that you need to understand. Okay? So in this particular case, I have expanded what the function looks like, and I have a Taylor series expansion. So that is actual algorithm, and the Taylor series expansion is going to be truncated right after there. Now compare. Well, yn plus 1 appears there, equal to yn on both sides, h times y prime, but here w1 times h times f. But what is y prime? Y prime is f, right? So the second term also matches if I make w1 as equal to 1. That's the process, matching process, okay? So it's a very trivial example, and so I just say that don't be equal to 1. And what is the truncation error? Well, the neglected term here is of order h squared. So the truncation error in the Euler method is of order h squared. That's a trivial one. So let's take a two-stage Runge-Kutta method. Okay? So V is equal to 2. Still an explicit method. Okay? So the expansion of the formula that I gave you will involve W1 K1, W2 K2. So there are two stages, K1 and K2. But K1 is going to be given by a time function evaluated at Tn yn. K2 is going to be given by a function evaluated at Tn plus C2h. So C2 is something I need to find. Okay? And yn plus A21 K1. So I need to find A21 also. But it can be sequenced such that I can calculate K1 explicitly, and then I use that K1 here, calculate K2 explicitly, and then I put back K1 and K2 and I predict what the next value is. So there is no iteration involved. So it is an explicit Runge-Kutta method, but it involves 4 constants in the algorithm: W1, W2, C2, and A21. I need to find all of them in such a way that this formula matches with the Taylor series expansion as accurately as possible. That's the same idea again. Okay? So I have now plugged everything into the formula. So I put W1 times K1, K1 is h times f, plus W times K2, but K2 I've replaced it by its form. Okay? Now, when I want to compare this with Taylor series, I need to realize that this function is evaluated at Tn plus C2h and yn plus A21 K1. This is where the algebraic manipulation gets tricky. So what I need to do is I need to expand this itself in Taylor series. Okay? So I have yn as such, and then W1 HFN, which is coming from there, and then W2 times h multiplied by whatever you see in brackets there is the Taylor series expansion. This is the same as this. Taylor series expansion for that. Okay? So you'll have the function evaluated at Tn yn, that is that, and then df dt multiplied by the perturbation in that, which is C2h, plus df dyn multiplied by the perturbation in that, which is A21 times K1, but for K1 I'm already substituting h times f. Okay? Now obviously there are other terms in the series inside that. Okay? So I'm going to just indicate that as a series expansion. Okay, so my goal is to match this expansion of the Runge-Kutta method with a Taylor series expansion, which I've given here. Okay, so the Taylor series expansion is yn plus 1 equals yn plus hfn, hyn, but yn is the same as fn, plus h squared over 2, y double prime, the second derivative over 2, that dt. But that is the same as df dt. This is what we said would give us problem. Okay, but the way that we handle this here is quite beautiful. We don't really need to calculate for every problem this problem-specific derivative, but we use the Taylor series expansion for that df dt is the partial derivative of f with respect to t plus partial derivative of f with respect to y dy dt. Plus the Taylor series tells us the next neglected term is of order cube. Do you have any questions on this? Make sense? Okay. So what is the next step? We do term by term comparison. Okay. So we take this term which matches with yn plus 1, and you take yn which matches with that, and you take hfn. In order to match it with that, what do we need? Be careful. W1, you cannot make W1 equal to 1 because there is also an HF here. Right? So everything that multiplies with HFN, all the coefficients there must be collected. Because all I want to do is make the coefficient that multiplies HFN to be the same ball. Okay? So the real condition is W1 plus W2 must equal to 1. HFN, HFN. Okay? And then what is the next term? The next term is df dt. Okay. df dt, I want to match that with the df dt term. So what should be the condition? Well, I have h here and h there, h squared, right? And I need the h squared is taken out of that. I have 1/2 here. So W2 times C2 must be equal to 1/2. Okay? Then we would have matched that particular term. Okay? Now sometimes it might happen that you have, by matching these, you are assembling a set of equations. And the number of equations that you assemble must match the number of unknowns in there. And if you don't have it, then you may need to go for another term or drop one of the terms. Okay? So that it's a careful matching process. Now if you look at the next term, df dy and dy dt is the same as f. dy dt is the same as f, right? And you have df dy which matches with this. So what do we need as a condition? W2 times A21 must equals 1/2. Okay. So these are the three equations that we write down. W1 plus W2 equal to 1. W2C2 must equal 1/2. W2A21 must equals 1/2 to match those three. Okay. So here we have a problem. What is the problem? We have 4 variables in 3 equations. Some may call it a problem, some may call it an opportunity. The opportunity is I have fixed one. I can fix one to be anything I want, right? And I can solve for the remaining 3. So that gives you like a whole class of Rankagada methods with just the coefficients. They will all be accurate to of order h cube, I guess, right? H cube, of order h cube. Okay. So this particular example is the beautiful one because it's not too difficult, but you understand that matching process. In 1 year, I think in somewhere around mid-90s, I gave a problem of developing a Rankagada method of 4th, 5th order embedded one inside the other, and Bia Huang was the only one who finished that problem. You needed to use, because the algebra of taking these derivatives and collecting these terms and matching them will run into 20, 30 pages, right? But he was smart enough to go to Maple and let Maple do all the work because it can take all these derivatives for you. You can gather the terms, right? And I kept that solution for a very long time. But we will see, yeah, sorry.
Scroll back up.
Yeah.
Those last 2 equations right there. Why do you not lose accuracy when you go from df dt to partial f, partial t plus partial f, partial y times partial y, partial t? If you're taking a Taylor expansion there and you're truncating that, wouldn't that affect your overall order of h cubed?
No. This is the Taylor series expansion.
Right.
Okay.
Right.
And the Taylor series expansion, the next neglected term is of order h cubed.
But then aren't you taking, df dt?
Oh, you're talking about
that.
why did I replace this with this?
Yeah.
Did I introduce any error?
Yeah.
The answer is no.
Okay.
Because that is an exact derivative.
Right.
Because all I'm doing is recognizing that the function f is a function of t and y.
Okay.
So if I have to calculate the derivative of df with respect to dt, all I need to do is use chain rule. Okay? So because this function is a function both of t and y, I first take the derivative, partial derivative with respect. So this is a total derivative. So here I'm taking partial derivative with respect to t, and then partial derivative with respect to y, and dy dt. So it's a straightforward chain rule. So there is no error involved in that expansion. Okay? So here are two sets of numbers that will satisfy those three equations. Okay? So this is the process of developing Rangakada class of methods. And typically present the results in this form in Lapidus and second. If you look at that, if you find these numbers, you should be able to construct the formula and then program it. It used to be a good exercise in the 90s, but nowadays you don't because algorithm is already available. Maybe there's an educational value here, but here is a fourth stage Rangakada method. The coefficient. Sorry, did you have a question? Yeah.
So you said you had to guess one of the parameters and then use that to get the rest essentially. What's the effect of your guess as far as like, I don't know, anything?
Right, that's a good question.
I know you're making a good guess.
I mean, even when you ask questions like that, that opens a path to find something potentially new, right? I have a degree of freedom. Why should I throw it away and pick an arbitrary value? Can I use it in Y space? And that is what led to the embedded algorithms that I'm going to show you later on, right? So there is no point in constructing. You can always construct one more constraint by matching the next term, right? But the problem is when we it's a good question. It triggers a lot of other things that I wanted to talk about and didn't. So when we expanded the second term df dt, I got two derivatives, right? You really do it by hand. When you do that, that is y triple prime. The third derivative, because it's a function of both t and y, you have to apply the chain rule more times. Okay. So instead of two terms there, the next h cubed term will have three terms there. So you need to match three terms. And if you have only one extra condition that you can use, there's no point in matching it with only one, because the truncation error in the other two will still be there. So for that purpose, it's okay to just say I'm going to pick arbitrary because I cannot achieve anything else. If I go to the next level, 2 stage, I need to find more coefficients. I need to match it with a more complicated expression. But the idea of embedding is then says, can I find two formulas, two Rangakada methods? One is a 4-stage, another one is a 5-stage. But the 4-stage method shares all the coefficients of the 5-stage method. Okay, that's why they say once embedded, the fourth order 4-stage method is embedded in a 5th-stage method. Okay, why would you want to do that? Obviously, with the same amount of work and a little bit of extra additional work for the 5th stage, you get two predictions. One is of order h to the power 4, another is of order h to the power 5. And compare the differences between these, we get an idea of the truncation error, which you can use for step size control. Step size control becomes an extremely easy issue with single step methods, because at will you can increase the step size or decrease the step size at any point. You don't have to worry about whether you have enough past values or not. Okay. So this is a 2-stage, and then the 4th order scheme, which is a 4-stage 4th order scheme. Okay. This is the most popular one, the 4th order Rangakada method. I think in an undergraduate course you would have seen it, but not gone through the logic of how it is developed. And RK45 is the one that is built into MATLAB. That uses the idea of embedding. So your question is at the right time. So what it does is it fits a 5-stage. It first develops a 5-stage method by expanding the Taylor series up to h to the power 5. And then you have some extra degrees of freedom, and you can say, okay, can I try to match the next term also? And if needed, I will introduce a few additional coefficients as well, okay, because it's a 6-stage method. And so the interpretation for this is, these are all the C values that you see here. These are all the A values for the 4 stages. And these are the weighting factors for the 4-stage fourth order method. So you have a prediction of yn plus 1 using a fourth order method. Okay? But using the same values of k1, k5, but calculating one additional function, k6. Okay? And so these are the coefficients of A that will go into that formula. Okay? And these are the weighting factors that you will see. You can predict fifth order accurate at y+1. Both are explicit methods. Okay? So this is a method that is built in, as I said, in MATLAB, and it's a powerful idea that you can embed one algorithm inside the other, and there are lots of them, of course, that have been developed. Do you understand the idea, what an embedding scheme is, what it does? So the idea is simple, but the algebra of developing these is quite tedious. Now, for semi-implicit methods, now, to determine the stability of each one of these methods, what do you need to do? You need to take the model problem, y prime equals lambda y, and get the growth factor between n and n plus 1 and see whether the growth factor is less than 1 or greater than 1. Okay? And the book by Seinfeld and Labdes has the stability bounds for each one of these algorithms. Semi-implicit and implicit schemes, we allow the coefficient matrix A to be either diagonal and below or full. If it's diagonal, then it's semi-implicit. If it is full, it is completely implicit. Okay? So this is the general framework for implicit. All we did is we changed I-1 here to V. So every K that you're calculating will have all the K's on the right hand side. Not only the K's up to that point, but beyond. Okay? So K1 in a two-stage method, K1 will have K1 and K2 on the right hand side. K2 will also have K1 and K2 on the right hand side. Yeah, you see it here. Okay, the expansion of that. So the matrix will be full instead of. So if it is strictly lower triangular, then you have an explicit method. If it is diagonal and lower triangular, it is semi-implicit method. But if it is full, then you have a fully implicit method. But otherwise, the idea is the same. The computational load is tremendously increased when you use a fully implicit method. Now this is one that's called the Gauss fully implicit method, where the coefficients are given according to this particular table. And there is a very interesting idea of how do you select these points. These turn out to be roots of certain orthogonal polynomials. If we have time when we talk about collocation methods, orthogonal collocation methods, we'll talk about Gaussian quadratures and why they are better than normal polynomial curve fitting. So, an excellent book for this whole topic is Lapidus and Seinfeld. The entire book is devoted to ordinary differential equations, algorithms for ordinary differential equations. I have a bibliography. I hope you are opening that and seeing what books there are. Maybe at this stage, let me just see whether I can open that and point out where I'm taking these materials. Because there was a question from PI guys. Is there a good reading source? The answer is there are several. And if you go to the course outline, I guess I just checked last night. We are doing reasonably well. We did algebra, nonlinear dynamical systems, functional approximations. We talked about one part of it, polynomial approximation. We'll come back, talk about orthogonal functions, ODEs, initial value problems, and the boundary value problems. Finite difference methods we have talked about. We'll see whether we can get to finite element and volume. Today I will hopefully, if there's time, get into partial differential equation classifications. Only 8 will leave out completely. That's CFD. You need a whole course for that, I think. But the books, okay, Anderson, Tannehill, and Fletcher is a good book for finite difference approximations. It is titled Computational Fluid Mechanics and Transfer, but it talks mostly about partial differential equations. And Kubitschek and Lavicek is a good one for bifurcation methods and boundary value problems. I'm going to take one of the algorithms from there today, shooting method. Okay, and Seidel is a good book for equilibrium to chaos. The continuation methods, they are all discussed very well there. And this is a problem I was fascinated with very early. It's called the dripping faucet problem, a model for a chaotic dynamics. And there are no equations there, just pictures. Okay? And what it talks about is the dripping faucet problem. What is that problem? Go to the kitchen faucet today and do this experiment. Okay, slowly increase the flow rate from completely shut situation and observe what happens. Initially, you will find that it drips gradually, right? Very uniformly, periodically, and just watch the sound. Okay, and If you increase it slightly, then you will see that it drips with a, what he calls the period 2. That's instead of saying tack, 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 he will say tack, tack, tack. And he interprets this as a root in the language of chaos. And I think in the 80s this was a very big topic, and it is a beautiful problem that talks about, and they did some actually pretty powerful experiments where they have a laser light going through that to detect precisely what is the time interval between two drops and how does that change, and then construct about Poincare maps and all that. So it's a very good introduction using a simple example that we can all relate to explore some complicated ideas. And the book by Finlayson on method of weighted residuals, I'll take some material from there also. Okay, where is that? Yeah, this one. Yeah, that's a good book also for method of weighted residuals, collocation methods, and stuff like that. So as graduate students, I guess they should be kind of curious enough to open these books and look at them from time to time. This is where I ran out of notes, so I'm going to just start writing it from now on. So what have we done so far? We have looked at finite difference methods for solving boundary value problems, whether it's a single equation or a system of equations. And what we did in that process is convert that into a system of algebraic equations, and then we say, okay, all the tools of continuation and stuff become helpful to solve a boundary value problem. For initial value problem, we took a different approach, okay, because the problem formulation requires us to be kind of marching in time. Okay, the differential equations can be the same depending on the conditions that are given. It becomes a boundary value problem or an initial value problem. So let me take an example of differential equation d squared theta dx squared. I will put this notes online after the lecture is over. Okay, so I have a second order ordinary differential equation. Okay, if I ask you is it an initial value problem or boundary value problem, you cannot answer at this stage because it's just a differential equation. Depends on what conditions I attach to it. So if I attach these boundary conditions, which is theta at x equal to 0 is 0 and theta at x equal to is 0. Okay, then what is it? It's clearly a boundary value problem. What is my domain of interest? From 0 to 10. Okay, so what I want to do is I want to construct a solution in x that goes from 0 to 10 for theta. Okay, and I want it to be such that it's 0 here and it's 0 on the other end. In between, the function that I come up with must satisfy that differential equation. Okay, so it must satisfy these boundary conditions at the end, that it must satisfy the differential equation, the function that in the intermediate. That's my goal. My goal is to find this. So what is the method that you would use that we've seen so far? Finite difference methods, right? What does that do? It simply puts a grid and replaces that equation at a typical grid point I. Okay, and what that does, I will write it down just quickly. Theta I plus 1 minus 2 theta I plus theta I minus 1 divided by x squared plus 2 theta I minus 2 equal to 0 for I going from 1 to n. So I start numbering it from here up to n. Because it's a directionally boundary condition at both ends, I know what they are, so I have only n unknowns and I get n algebraic equations. Fairly straightforward problem. So I can assemble the matrix and solve that. Because the boundary value nature of the problem at every theta I depends on values on either side. And that's what makes it different from an initial value problem where I know the values only at one end and I need to project from there and I can integrate. The future value is not influencing the current value. The current value is influencing the future value, right? But boundary value problem, the trajectory must evolve in such a way that it lands exactly at this point. Okay? So now the question is, can I use an initial value method that I have developed, Ranka-Kada method or a multi-step method, to solve this problem instead of finite difference method? Second question would be, why would you want to do that? When you have a method that works, why would you want to do that? Right? One of the reasons why we might want to do that is, we know that the truncation error here is of order, it's square. Okay, so the only way that we can get more accurate result is put more grid points. But what did we learn in the initial value methods? I can develop a method which is of order h to the power 4, h to the power 5, right? So I have very accurate methods for integrating with few additional calculations. So very efficient methods, right? So if I have to increase the order of accuracy here without increasing grid size, what would I do? Louder? I cannot hear. Yeah, whatever the idea is. And we'll see whether it works, it makes sense, or it doesn't. What do we know about approximations for derivatives? When we develop the finite difference method, we have a 3-point central difference method, we have a 5-point central difference method, we can have a 7-point central difference method, right? That's how we increase the accuracy by putting a higher degree polynomial, right? So we can, in principle, have an h to the 4 scheme that will involve not only theta I minus theta I plus 1, but it will involve theta I minus 2, theta I plus 2, right? That is, in fact, in the table that you have. What would be the problem if I use that? And the boundaries, you all immediately see the problem, right? So when I take that and apply it here, I need 2 points on the outside of the boundary, and I don't know what they are, okay? So that path is really not very productive. There are some papers that address that, but it has been kind of abandoned. So the most popular one is the central difference, second order central difference scheme. But the shooting method addresses this problem using and treating it as an initial value problem, okay? And I think I would like to extract the idea from you. Okay, what is the idea of a shooting method? The shooting method is like shooting a cannon. Okay, so in solving this problem, I know what the value is, but I don't know what the slope is. Right? So imagine I can control the angle of that initial projectile. Okay, and I have to shoot it in such a way that it lands exactly at the other boundary condition. Okay, so what I'm doing is I'm giving myself some degree of freedom to change this so that I land up exactly that way. How can I do that? Then I'm converting a boundary value problem to an initial value problem, but using a trial and error method, I'm going to find a solution to the boundary value problem using an initial value method. So if I convert this into initial value problem, what would I do? I would define y1 equal to theta and y2 equals d theta dx. And then these are two definitions for variables. I'm converting a second order equation to two first order equations. Then I can use it with my initial value problem solvers. Then I will have dy1 dx as equal to y2, right? Because dy1 dx is the same as d theta dx. D theta dx is y2. Okay? And then dy2 dx will be equal to what? Well, dy2 dx is d squared theta dx squared. D squared theta dx squared is this. So I can write it as 2 minus 0.2 times theta, but theta is y1. Right? So I have two first order equations. I converted the second order equation to first order equations. What are the two boundary conditions? What are the two conditions? Initial conditions, I should say. Well, theta is the same as y1. So y1 is equal to 0 at x equal to 0. What about y2? Y2 is d theta dx, and I don't have a value for that. Okay, so I'm going to make that as equal to alpha, an unknown. I'm going to find what is the value of alpha that will match the condition that I must meet. What is the condition I must meet? I must meet this condition at the other end. Okay, now I forget that it is a boundary value problem. I have an initial value problem. I have two numbers here. One of them is a guess. Okay, I use that and use that RK45. Make a call to RK45 and say integrate it from 0 to 10. So t is like my x, right? And it will pick y1 and y2 at every one of those along the way. And at the end, I need to examine only which one? y1, right? Because I need to examine whether y1 is equal to 0. Okay? So what I do is I examine y1. So the way it works is guess 1, I guess alpha 1. Okay? And I shoot, and what I get is y1 at 10. I'm going to call that number as beta 1. Okay? I make a guess for alpha 1, but alpha 1 is nothing but y2. 2 at 0. Okay? So I make a guess for the slope y2 at 0, I shoot, and I get a look at y1 at 10, and I call that number as beta 1. If it is 0, I'm lucky, I made the right guess, right? What can I do if it is not 0? You will guess another alpha, right? So guess 2. So y2 is equal to alpha 2, and I will get a beta 2. That's not also 0. What do I do next?
Depending on which direction I guess to go.
That's it. See, numerical analysis is nothing but intuition, right? It's not as difficult. Okay, you made 2 guesses, and you know how it is responding to changes in alpha, right? And can you then devise a scheme that will allow you to make a 3rd guess that's better than the first 2 guesses? Why not secant method? Why not regular falsi method? Right? Any one of those methods that you can use. Okay? So a linear interpolation. Use linear interpolation. Okay? Secant method. What does that look like? It looks like alpha 3 minus alpha 1 divided by alpha 2 minus alpha 1 equals beta 3 minus beta 1 divided by beta 2 minus beta 1. Okay, so what is alpha 3? That is the next guess that I want to make. What would be beta 3?
Never happened.
You would like it to be 0, right? So whatever the value that's given to you. So in this particular case, I want it to be 0. So that equation has only one unknown, alpha 3. I've generated the beta 1 and beta 2, guessing through alpha 1 and alpha 2. So that's linear interpolation. So I can guess the 3rd alpha. In this particular problem, do you think it will give you the right answer? How many of you think it will not? The 3rd guess is not enough. We need to make more guesses. You are hitting the right keyword I'm looking for. So the answer to that question lies on whether this problem is linear or non-linear. Okay. In this particular case, it is linear. It will work. It will give you the 3rd guess. Will give you the right solution. Why? Because you have 2 trajectories. Okay, and you can always superpose those 2 trajectories to construct a 3rd trajectory that will also satisfy the differential equation because linear superposition. But what you are doing is you are superpositioning in such a way that boundary cancels out and lands on exactly 0. So the entire profile will adjust itself and will give you the solution in the 3rd trial for any linear problem. If it is a non-linear problem, then it's not true. Yeah.
Is it? I mean, I guess when you have a linear problem, is it possible for that method to give you like a trivial solution, or will you always get a good guess? Like for example, a trivial solution where theta is 0 the whole way down. You know what I mean?
Mm-hmm.
It's 0 from on the bound of 0 to 10. Like, can you run into that problem?
Well, the question, I guess, guys online was, can you have a trivial solution such as theta equal to 0 everywhere for the wrong choice that you make for alpha? If I make alpha is equal to 0, will I get the trivial solution? That's the question. Okay? Let's look at this problem. Okay? So what I'm saying, what you're saying is, I want the trajectory to take off like this because I want the derivative to be equal to 0 at this point. Okay? The only time when that will stay on this one is if the original differential equation has no source term, no exciting term. Okay? If I set instead of 2 equal to 0, then what is the one function that will satisfy the differential equation and the boundary conditions? So homogeneous equation, the right hand side is 0 with homogeneous boundary condition. So theta equal to 0 is your solution. If you have a forcing term, that means it will never happen. Okay? So your initial guess may take off from here and give you a solution that is not at all the solution that you want, because you are enforcing the derivative to be equal to 0, and the curve looks like this. But that curve satisfies that differential equation. What it does not satisfy is the boundary condition. Okay? And then you'd make a second guess, and your guess may be something like this. Okay? And that does not also satisfy it. But the entire curve will satisfy your solution, the differential equation. And because it's linear, you can adjust, you can add them up in such a way at the boundary you bring this to 0. Then the profile would be perfectly satisfied.
It's not homogeneous, you will never get the difference.
Yeah.
Are you restricted to alpha values of a certain
No.
of a certain number? I guess using the secant method, can you have, if you have, I mean, a theta versus x profile that dips below the x-axis for the entire stretch of the solution, but both of your alpha values are positive, so your initial slopes are positive
Right.
for alpha 1 and alpha 2.
Yeah.
Will
I understand your question. Let me just open up one more page and draw the picture. So what you're asking is, the question is, if the solution, let me put that as theta equal to 0, this is from 0 to 10 for x. If my solution entirely is like this, in the negative space, but I make two guesses that are both in the positive, this is alpha 1, this is alpha 2. Okay, so I get one solution like this, and I get another solution like that. Will superposition give you the exact result in the third attempt? Is that what you're asking, right?
Yeah.
I guess I shouldn't make them go to 0 there. So it goes somewhere there, and it goes somewhere there. Okay? The answer to that question is still, as long as the problem is linear, I could linearly combine it such that this boundary condition is satisfied, and it will flip itself. It will give you the exact solution, because each of the curves satisfies the differential equation. It's not true for nonlinear method. For nonlinear method, you need a few secant iterations before you will get a solution. But the method is very effective. Why is it effective? Because I get accurate, fourth order accurate, fifth order accurate solution, depending on what RK4, RK5 method that I use. Okay? And I don't need as many time marching schemes, in this case X marching schemes. That's the basic idea behind shooting method. Okay? It's a very, very powerful method which combines initial value and boundary value problem solutions. Question, yeah?
So like for nonlinear problems, will there be like two solutions?
Yeah, that's a problem. The moment you open up the nonlinear problems, all the problems that we have discussed, that's why we spent so much of time earlier part of the course. So you have a nonlinear boundary value problem, it could have multiple solutions.
I will be able to detect like all the solutions.
That's the one I'm going to talk about. Okay, so continuation methods for boundary value problems. It's a beautiful idea. So it's going to be.
Problem was attacked.
That problem is one example. It's a boundary value problem. It has multiple solutions, and we did not use the shooting method. We used the finite difference method, right? But whatever the method is, the physics of the problem dictates multiplicity of solutions. All these methods should capture all of those. Okay. So what would happen is, if you're using the shooting method to solve the Radu problem, depending on your guesses for alpha and the iterative sequence, the secant method, it might catch on to either one of those two solutions or three solutions. Yeah. Okay, so I'm going to put a few more variations before I delve into the big problem, the challenging problem. And the first variation is I have a third order problem here. Okay. D cube y divided by dx cube plus d square y over dx square plus y is equal to 5. And I have three conditions: y of 0 equal to 0, y prime of 0 equal to 1, and y at 1 is equal to 5. Okay, so that is also a boundary value problem. My domain of interest is from 0 to 1 because I have the condition given at 1. And of course, it's a third order system. So can we use finite difference method for this? we can. We need to find an appropriate derivative approximation for the third derivative, okay, which might involve more than 3 points, right? So it might create some challenges in handling the boundary conditions, but finite difference method certainly is available. But we can also convert that into 3 first-order equations, okay, and use the shooting method. So how would you go about implementing shooting method on this problem? What would you guess and what would you match?
You guess for the second one, zero.
What?
You get y1 equal to y, y2 equal to...
You go through the process of converting, right? So you will say y1 is equal to y, and y2 equals y prime, and y3 equals y double prime, and then you will have dy1 dx is equal to y2, dy2 dx equal to y3, and dy3 dx will be equal to 5 minus y1 minus y2, something like this. Okay, and you will have conditions for those. Those conditions are y1 at 0 equal to 0, y2 at 0.
And that's y1 minus y3.
Did I make a mistake?
The final
No, y1 minus y2, because y2 is d squared by dx squared. And this third derivative,
y2 is the x dy dx.
y2 is dy dx, yeah.
Right, so the y3 is...
Oh, yeah, sorry, y3, that's right. Thank you. Yeah. Okay, so in terms of the initial conditions, I have y1 is equal to 0, and y prime, which is the same as y2, is equal to 1. And then I have at the other end, the condition is y1 at 5 is equal to 5. So how would I set up the shooting method for this one? What do I need to guess? What do I need to validate? You need to guess y3. Okay, so y3 at 0 is equal to alpha. Okay, and what do I need to check? I need to check y1 at the other end. 1, right? That 1 is equal to 5. That will, I will set that as equal to beta, and then it's the same procedure. Okay. Suppose I change the problem to the following. Oops. What do you immediately got it? You shoot backwards, right? Why do you shoot backward? If I shoot forward, I need to guess 2 values, right? So if I give you 2 values on this side, then okay, it's easier to guess on the right side and then shoot back. You can integrate these. All these algorithms will work. That if you post them in an autonomous fashion, they will all work, whether it's forward integration or backward integration. Okay, so you can do that. So the next question would be, what would I do if I have 4 equations and I give 2 on one side and 2 on the other side? Flip a coin. You don't have an advantage in choosing either one or the other. You need to guess 2 values at one end. You need to match 2 values at the other end.
Could you guess one on each side, like iterate back and forth, and not work?
You can do that. So that's what I'm going to do in the next class. Hopefully I will type up the notes so that we can go through that. It's a very interesting implementation, generalization of the idea that borrows a lot of ideas of extended system, continuation methods and stuff, right? So we will see how to implement 2. Yeah.
The shooting method couldn't be used for partial differential equations. Like if you had, now you're talking about in x direction, but if you had x and y, or as long as you have, as long as it's still a linear problem and you have the correct number of conditions specified, you can still shoot.
I have not seen that idea implemented. The challenge that I would see is in a partial differential equation, you have domains, so the boundaries would be actually a line, not a point, right? So you need to guess an entire function on one side
Right.
and match that with the other function on the other side. So may still be possible, but I haven't seen anybody implement that.
Say if it's linear, you should,
Um,
as long as it's linear, right?
If it's linear, it gives you some flexibility in using superposition and makes it, I guess, possible to converge faster. Okay, so I think we'll stop there today, and then in the next class I will complete the shooting method for multiple system of equations, and then we'll move on to partial differential equation, classification of these, and finite difference method for them, and collocation methods. How many showed up?